Welcome back, everybody. Let's continue to talk about hypothesis testing. In this video, we'll go through our fourth and final example. We're going to continue to talk about hypothesis testing for the rest of the semester, but at least in this video, we'll finish up our basic introduction to the subject. Let's take a look at the fourth example. By now, you should be seeing that all of these examples are essentially the same. And all that I can do is make up some different research situation and make up some different numbers and then ask you to go through the 4 steps. The one little detail that makes this example different is that now we're going to use a different alpha level. In this case, we're going to use an alpha of 0.01. Remember, that alpha level is very important. It's that alpha level that determines how much evidence we need to find statistically significant results. In other words, it shows how much evidence we need to reject the null hypothesis. Keep this in mind too. Theoretically speaking, that alpha level determines the probability of us making a type 1 error, and we don't like to make type 1 errors. We know that in psychology, sociology, social work, education, and many other fields, we tend to use an alpha level of 0.05. That means over the long run, we make type 1 errors about 5% of the time. The people in those fields tend to agree that that's okay, that's satisfactory. However, there are some people in other fields where they believe that's far too many type 1 errors. For example, in medical research, they almost always use an alpha level of 0.01. That means in order to find statistically significant results, they need more evidence. However, over the long run, they will only make type 1 errors 1% of the time. So let's change the views and then work on this example together. Let's see what we're dealing with. It says a medical researcher believes that babies born addicted to crack tend to be lighter than normal healthy babies. Remember, everything that we know right now, at some point, someone had to discover it. And at one point in history, when there was a crack epidemic, people were born addicted to crack because their mothers were addicted to crack. And we were finding that those babies had problems, all kinds of problems. Well, one problem was that they were born lighter than average. And birth weight is a good predictor of overall health. So in general, you don't want to give birth to an underweight baby. Well, this research is about that topic. It says, regarding the weight of healthy babies at birth, let's assume that the population mean weight is 8 pounds and the standard deviation is 2. The researcher finds that a random sample of 30 addicted babies has a mean birth weight of 6.5 pounds. So descriptively, we see a difference between 8 pounds and 6.5 pounds. But remember, there are 2 competing explanations for why we see that difference. One explanation is that the population of babies born addicted to crack is indeed lighter at birth than normal healthy babies. But another explanation for those results is that that difference between 8 pounds and 6.5 pounds is the type of difference we would expect just due to sampling error. So our job is to see if we can effectively rule out sampling error as a viable explanation for those differences that we actually see. We're going to do a 2-tailed test with an alpha of 0.01. When we're using an alpha of 0.01, we need lots of evidence to find statistically significant results. Let's go ahead and start at step 1 by stating our hypotheses. Remember, we have a null hypothesis and also an alternative hypothesis. And these hypotheses are always stated in terms of population parameters. So then I ask myself, mean what? What is it I'm measuring? Well, I'm measuring birth weight. So population mean birth weight. And then I ask myself, whose birth weight? I already know the population mean birth weight for normal, healthy babies. What I don't know is the population mean birth weight for those babies born addicted to crack. I'm trying to learn about that population based on this sample of 30 babies. So population mean birth weight / babies born addicted to crack. I'll just put a /C. Remember, the null hypothesis states there are no differences between these groups. So the null hypothesis would state that the population mean birth weight for the babies born addicted to crack equals 8 pounds. Of course, we are doing a two-tailed test, so I'm setting up these hypotheses to conform with the two-tailed test. That would mean that the alternative hypothesis would state that the population mean birth weight for the babies born addicted to crack is something other than 8 pounds. Remember, we have determined for our class that if theoretically your results can go in either direction, you should be doing a two-tailed test. So I'd ask myself, is it possible that these babies born addicted are lighter than normal healthy babies? Yes, that's possible. Is it possible that these babies born addicted are heavier than normal healthy babies? Yeah, theoretically that's possible. Well, if both those results are possible, I should probably be doing a two-tailed test. And that's why we're doing a two-tailed test. So let's move on to step number 2. Step 2 is all about figuring out how much evidence do we need to reject the null hypothesis. Before we mark off those critical regions, we like to mark up this distribution so we know what we're dealing with. First of all, this is a distribution of sample means. We're not dealing with distributions of individual scores anymore. That's a distribution of sample means. And that distribution of sample means is being created based on this parent population. So that parent population is giving birth to this distribution of sample means. And therefore, it should have similar characteristics. If that parent population has a mean weight of 8 pounds, then this distribution of sample means will have a mean of 8 pounds. Keep in mind, we create that distribution of sample means based on that null hypothesis being true. If that null hypothesis is true, we would expect lots of sample means right around 8 pounds. Right up there, next to that axis, we are listing sample mean values, and right below it, we're going to list z-scores. If we were to transform 8 pounds into a z-score, z would equal 0. We also know that in that sampling distribution, there's some variability. And that variability is measured by the standard error of the mean. And we need to know the standard error of the mean in order to transform our sample mean of 6.5 pounds into a z-score. So we might as well compute standard error of the mean right now. We can find the standard error of the mean by taking the standard deviation from the population and dividing by the square root of the sample size. The standard deviation from the population of individual scores is 2 pounds, and we know that our sample size equals 30. So in the next step, let's figure out what the square root of 30 is. We're going to have 2 divided by, I'm going to type in 30 and then hit my square root key. That equals about 5.48. 5.48. And then finally, let's take 2 and divide by 5.48. 2 divided by 5.48 equals about 0.36. 0.36. That standard error value is relatively small. What we're saying is, on average, the sample means will differ from 8 pounds by only 0.36 pounds. So there's not a lot of variability from one sample mean to the next. Well, it looks like we've got everything labeled up pretty well. Let's remember why we're actually here in step 2, and that's to locate the critical region or regions. We're doing a two-tailed test, so we have 2 critical regions. And we're using an alpha of 0.01. That means we're going to mark off where there's 0.5% of the sample means in each tail. So we're really pretty far out there in the tails. So I'm going to mark off 1 critical region right here and 1 critical region right here. We now need to find where there's 0.5% in each tail. I find that students sometimes run into trouble when they're dealing with these really small numbers. And in our z-table, we need to make sure we look up the right thing. I want to find the proportion of area in the tail that equals 0.5%. So let's just use our calculator to figure out exactly what that looks like. I'm going to take 0.01, which is 1%, and simply divide it by 2. That equals 0.005. That's what we want to look up. The proportion of area in the tail equal to 0.005. That's 0.5%. I know I've mentioned before, some of you can see that very easily in your heads, other people can't. So we're looking for 0.5% in this smaller portion in the tail. 0.005 in the smaller portion. So let's start cruising down. We know it's pretty deep in the distribution. Now don't get confused when you come around here and you see 0.05. We're looking for 0.005. So I'm going to keep going down, keep going down. Now I'm getting close. Here I see 0.0051 and 0.0049. And like we saw in a previous example, those two values are equally close to 0.005. So we're going to have to choose between a critical value of 2.57 or a critical value marking off our critical region of 2.58. And you might recall I told you that for our class, our policy is that we will pick the value that requires more evidence. We will pick the critical value that pushes out those critical regions just a little bit more. So between 2.57 and 2.58, I'm going to pick 2.58. So let's go ahead and mark off those critical regions. Over here on the right-hand side, I have 2.58. And on the left-hand side, I have negative 2.58. So we're back in that same situation. I need to figure out where is 6.5 pounds. Is 6.5 pounds the type of sample mean that we would expect to find right in here? In other words, is it the type of sample mean that we would expect to find just due to sampling error, just by chance? Or is 6.5 pounds going to be in this little region right here? One of the sample means that is very unlikely to be found just due to sampling error, just due to chance. Well, there's only one way to know for sure, and that is to transform 6.5 pounds into a z-score. So let's do that. So x bar is 6.5 pounds. We'll stick that into our formula. We're going to subtract the population mean. That's always the value based on our null hypothesis, which is 8 pounds. So those are the differences we actually see. Those are the differences we actually observe. In this C formula, we now divide those differences by the differences we would expect just by chance. Remember, it's the standard error of the mean that measures differences between sample means we would expect just due to sampling error. So I'm dividing by 0.36. What we're left with is negative 1.5 divided by 0.36. And we'll use our calculators to help crunch that out. So I'm going to take 1.5, make that negative, and then divide by 0.36. That equals a z-score of negative 4.17. My friends, I hope you recognize that's a large z-score. That is 4.17 standard errors below the mean. That means that weight, 6.5 pounds, is 4.17 standard errors below the mean. So negative 4.17. Where is that in our distribution? Right here in the middle, we have a z-score of 0. Right here, we have a z-score of negative 2.58. Negative 4.17 is quite a bit more to the left. Keep this in mind. Theoretically speaking, that tail moves on forever. So negative 4.17 is somewhere right around there. We are clearly inside this critical region. We have surpassed that critical value of negative 2.58. So that provides us with all the information that we need to answer those 4 critical questions that I always come up with at this point. With the first question being, is our sample mean inside the critical region? In other words, is our sample mean inside the rejection zone? And the answer is yes. Now the good news is the follow-up questions that I'm going to ask, they all have an answer of yes as well. So, should we reject the null hypothesis? Yes, we should reject it. So I'm going to cross it out. And I'm going to check off the alternative because we now embrace the alternative. And let's take a chance to just look at it and see what it says. The alternative hypothesis says that the population mean birth weight for the babies born addicted to crack is not equal to 8 pounds. And we have evidence to show that it's less than 8 pounds. Next follow-up question. Do we have statistically significant results? Yes, we do. So let's make a little note of that. These babies born addicted are statistically significantly lighter than the normal healthy babies. Next follow-up question. Remember, let's look at the big picture here. Is there at least a possibility that we're making a type 1 error? Yes, there is at least a possibility. Remember, this is a distribution of all possible sample means. So just by chance, we will sometimes find a sample mean of 6.5. We won't find sample means of 6.5 very often at all, but just by chance, sometimes we will. Well, we need to be reasonable. At some point, we need to draw the line and conclude that we have enough evidence, and we do have enough evidence in this case. That's why I say we have effectively ruled out sampling error as an explanation for our results. Have we conclusively ruled out sampling error as an explanation for our results? No, this procedure does not allow us to do that. So don't necessarily get too caught up in this whole idea that we might be making a type 1 error. Yes, we might be making a type 1 error, but the probability of making a type 1 error in this situation over the long run is just 1%. Remember, we're using an alpha level of 0.01. So the probability of making a type 1 error over the long run is really pretty small. There's just one more thing we need to do to prepare for writing up our results in step 4. We're going to get to the point where we need to say something about the probability of finding our results just by chance. And we're going to have to pick between the probability of finding our results just by chance being less than 1%. You see how I'm listing that in terms of the alpha level? We're going to have to pick between that and the probability of finding our results just by chance being greater than 1%. Keep this in mind, area equals probability. We found that our sample mean was in this small little area, so it should be associated with a small probability. Well, what's small? A probability less than 1% or a probability greater than 1%? A probability less than 1% is small. So that's what we will list in our results. And that's important. It's important that we make that decision correctly, because when people read p less than 0.01, they will know that the results are statistically significant. So here's an example of how we can write up the results. Remember, there are 4 things that we need to address at step 4. You need to tell me, are you going to reject or fail to reject the null hypothesis? You need to explain to me what you found in everyday language. You need to show me how would these results appear in a journal article, and you need to compute the most appropriate measurement of effect size, which in this case is Cohen's d. Let's talk about that first point. We did decide that we will reject the null hypothesis, and here's how I would put that into context. That sample mean of 6.5 pounds was within the critical region. This sample mean, 6.5 pounds, is unlikely to be found if the null hypothesis is true. In other words, our sample data is inconsistent with the null hypothesis, so we reject the null hypothesis. Everyday language, what did we find? Babies born addicted to crack are significantly lighter than normal, healthy babies. How would that result appear in a journal article? Keep in mind, we transformed 6.5 pounds into a z-score, and we found a z-score of negative 4.17. So we list z equals negative 4.17, p, the probability of finding these results just by chance, is less than 1%, showing that that result is statistically significant based on a two-tailed test. So to this point, we have concluded that babies born addicted are lighter than normal healthy babies. Well, how much lighter are they? Of course, we're very familiar with measuring people in terms of their weight in pounds. So in this case, we can see that the babies born addicted were 1.5 pounds lighter than the normal healthy babies. So this is one of those times where the measurement of effect size isn't quite as important in helping us determine the size of the effect. But nonetheless, we're going to compute the effect size because it is a standardized effect size. And across all studies, it helps us determine the general size of the effect. So as I just mentioned, in this case, the difference between the sample mean of 6.5 pounds and that population mean for normal healthy babies of 8 pounds is a difference of 1.5 pounds. We're going to divide that by the standard deviation on that measure. And above we see that the standard deviation when it comes to weights of babies is 2 pounds. Negative 1.5 divided by 2 equals negative 0.75. So what we're finding is that these babies born addicted are about 3/4 of a standard deviation lighter than normal healthy babies. That's getting to be a relatively large effect size. Just to get a sense of the magnitude of that effect, let's think about it in terms of IQ scores. We know that the average IQ score is 100 and the standard deviation is 16. 3/4 of a standard deviation would be 12 points. Imagine having 12 points slashed from your IQ. That would be going from an average IQ of 100 to an IQ of 88. I know I would not want to have that done. But essentially the same type of thing is being done to these babies when they're being born 3/4 of a standard deviation below the normal healthy weight. All that really means is that they're being born with at least one disadvantage, and we hope that they'll be able to overcome that later in life. So that wraps up our fourth and final example for this particular chapter of our course. I hope by now you're starting to feel more comfortable with the 4-step hypothesis testing procedure. It's important to go through several examples, and it's important to master each step. As I've said before, hypothesis testing isn't going away. At this point, we're going to start learning several new inferential tests. And the beauty of that 4-step procedure is that we can use that procedure with a variety of different inferential statistical tests. Well, I think that's enough for now. I'll see you in the next video. In the meantime, be safe.